Full. Oh, okay, so yeah, I'm recording now. And yeah, if you have any questions at any point during the presentation, feel free to write in the Zoom chat. There will be breaks, I guess, for the questions. So don't worry if it's not answered immediately. We will get to it during this kind of question breaks. Yeah, also if you have like any technical issues, I guess, with Zoom or with something else, uh, write also in the chat, and I will be hopefully able to fix it. Uh, so yeah, I think this is most of the organizational things. If you have any kind of questions or concerns right now, please let me know. Otherwise, I think we can start. Okay, so I don't think we have any questions. So Nathaniel, the floor is yours. Thank you again for joining.
No, thank you. Yeah, so thanks for joining, folks, and for the interest. I'm going to be talking about structural causal models in PyMC. Let's see if I can move this forward. The broad pitch of the talk will kind of be that structural causal models impose extra statistical constraints on the derivation of valid causal claims from data. And so pedagogically, I think there's a really nice presentation of like this criteria by walking through how to implement SEM models in a Bayesian setting. So the pitch here is sort of broadly that we're going to outline the development of structural causal models in the Bayesian setting, which will allow us to highlight the use of the do operator for deriving valid causal claims. So that's the broad pitch. Some sort of preliminaries. Who am I? I'm a data scientist at Personio. I'm a Bayesian statistician and somewhat reformed philosopher. The main thing that's probably important for people who'd like to follow along, you can find, if you go to the link for this talk, you can download a Python notebook, which will have the code for the models that we will discuss today, and additionally the data set which we were going to fit our models on. I think you should be able to scan the QR code to get to my website for that if you haven't already. But additionally, you can go to the link in the Zoom chat. Okay, great. So the sort of broad agenda of this talk is kind of split into four sections. And the kind of thrust of it is moving between different lenses on the problem of causal inference in some sense. And we're going to have like a sort of abstract formulation of causal inference with DAGs. We'll look to a concrete implementation of those, and then concrete in terms of code. We're going to step through sort of models of rising complexity. So I'll do this trajectory from abstract to concrete to code with respect first to an instrumental variable causal inference question or causal inference model. Then I'm going to introduce factor structures and confirmatory factor models as a stepping stone towards fully fledged structural equation models in the Bayesian setting. And once we've established what those models are and how to implement them, then we'll discuss how to implement sort of causal how to derive causal estimands using a do operator in the PyMC context. I hope that's clear. I'll try and pause at the intervals between each of these sections in case there's any clarifying questions throughout. But yes, otherwise throw questions in the chat as they occur. So this is somewhat of a maybe a philosopher's introduction to causal inference at the top of this presentation here. And I'm kind of taking like inspiration here from the fundamental result in Judea Pearl's book Causality is a completeness proof. Completeness proof that shows the relationships between his graph algebra and probabilistic algebra kind of writ large. And this is sort of familiar to a philosopher or a logician in the sense that a completeness proof constrains the set of admissible formulas within a logical language. And the way I kind of see Pearl's project is that he's sort of trying to derive a set of rules of construction for a kind of grammar or logic of causal inference. So in the same way that in a logic, there are a set of well-formed valid formula, in the causal inference problem, there's a set of admissible causal inference graphs, right? Or admissible graphs which would license causal inference on those structures. The title slide, if you should be able to press the directional arrows and it will move across, I think. So there's this nice quote here about like what the sort of logician's project kind of is from Wittgenstein. And so the idea here is that syntax, a logical grammar, or the syntax of a causal grammar, is such that it will define connections that are admissible and exclude all nonsensical structures. So in the Perlian project, this is structures which will not license a causal claim. That's the thought here. So that's like abstractly, Perl starts with these sort of DAGs. This is one of his languages, so to speak. But he also has these non-parametric phrasings of the DAG as well. So these are highly abstract vehicles that circumscribe different data generating conditions. And these are the DAGs here that I'm going to show here on the slide are privileged DAGs in a certain sense. The DAG on the left is a DAG which defines the conditions of a random control trial, where R here is randomization, Z is a treatment, Y is an outcome of interest, and X is a potential confounder or set of confounders. If our data generating conditions match the DAG on the left, we can cleanly read off the treatment effect of Z on Y because it's unconfounded and held to be such due to the effect of randomization. The DAG on the right is also a privileged DAG because it's a certain type of problem. And under the conditions that are on the right, our treatment effect of Z on Y is confounded by the influence of X. And we need to use the instrumental variable, IV in this case, in a particular fashion to purge the inferences about Z of the biasing influences of X. So that's all highly abstract and somewhat intimidating to come at, but you can phrase that more concretely when you look at it as sort of regression models. So on the left, you see that a simple regression fit of Y over Z will derive a causal treatment effect for Z on Y without having to do anything too fancy. If your data is generated by the graph on the right, then you have to do something a bit fancier, traditionally two-stage least squares, where you first try and predict Z hat as a function of the instrument, and then substitute Z hat into your model for Y, thereby trying to derive the sort of unbiased estimate or causal estimate of the effect of Z on Y. Okay. This model can be also phrased in a Bayesian way. And this is kind of what I want to talk about. Because if you phrase these causal inference problems in a Bayesian setting, it's kind of different from the sort of quasi-experimental designs that you might have seen before, using sort of simple regression designs. In the Bayesian setting, you're sort of almost necessarily starting with trying to model the joint distribution of all the relevant variables in your problem set. So the Bayesian phrasing of the IV model is a multivariate normal likelihood, and you set it up in such a way that you have two sort of equations within it. Those two equations are sort of your proxies for the two-stage least squares equations that you might have seen before, but you explicitly instantiate those equations as draws from a multivariate normal with a particular covariance structure, sigma here. And so in this phrasing, the point I want to drive home is that even a simple IV design is a structural causal model in the Bayesian setting. The crucial component of the IV design in this setting is the covariance structure of the joint distribution and the instrument's theoretical validity. So that's like you can think about that in terms of the relevance or exclusion restriction sort of criteria for designing a good IV model. Or you can consider that as the instrument strength as being an important component of that. So you can derive the F score for your instrument. But the Bayesian estimation strategy is different from the two-stage least squares because it seeks a sort of parameterization where the potential outcomes are conditionally exchangeable. And generally, a Bayesian model is going to seek to take the joint distribution of our data set and factorize it out in such a way that we can derive conditional exchangeability of our outcomes, and in particular, in the causal setting, conditional exchangeability of the potential outcomes of the y value under the treatment conditions as they vary. Okay. So in a model, in the PyMC setting, this is how you would implement the IV design. So for those of you who haven't seen PyMC model before, this is what it kind of looks like. You set up your priors. These are beta priors for each of the covariates in our two regression equations that we have embedded in the Bayesian model. We set up priors for the correlation or covariance structure as well. We then multiply our beta priors by the X data or the Z data that we have, so the instruments or the observed covariates that we want to predict the outcomes Y for, and we stack them into a multivariate normal likelihood, and then sort of sample from in the MCMC fashion to derive our posterior distributions. Okay, so that's a lot of like kind of table setting, I think. The point I kind of want to make here is that there is like a requirement in causal inference for building credible maps between the model we have at hand and the world and the data generating conditions underneath it. Pearlian DAGs are a very useful tool for trying to characterize the minimum structure of the world that we need to ape in our model specification. There's also sort of nice, we won't touch on it too much in this talk, but there are rules of the do calculus which will allow you to circumscribe what are the minimum viable DAGs that will license causal claims in such a setting, in such a data generating setting. And this is kind of brought out, I think, really nicely in this book called Theory and Credibility by Ashworth, where they give a tour of different sort of causal inference methodologies, and they highlight the sort of mapping that needs to be true between the model of the world and the mathematical structure that you're defining. And they kind of argue that a similarity or a commensurability between the model itself and the research design or the world needs to exist. And like, so in some sense, what we're saying here is that you can start really abstract with these non-parametric graphs or these non-parametric sort of functional equations. You can make it slightly more concrete with, say, two-stage least squares in one instance, or a regression model of some kind or other. And again, you can rephrase that in a Bayesian setting. And these are all sort of equivalent ways of looking at it, but they're ascending a hierarchy of abstraction, or maybe descending a ladder of abstraction. The DAGs are the most abstract phrasing you can have, and you want to pull that down and make it as concrete as possible in a mathematical representation of your joint distribution that you care about. And Bayesian networks and Bayesian models within PyMC are a really efficient way to try and model or represent that joint distribution that you care about for deriving causal conclusions. Okay, I think I've set the table a lot. Now I'm going to talk about confirmatory factor structures and confirmatory factor models in general. Because, let me step back. So the point I was trying to make about the joint distribution, Bayesian settings in general Bayesian modeling in general will rely on Di Finetti's representation theorem to try and pull out a nice representation of a complicated joint distribution. By conditionalizing on a richly structured prior, we try to decompose or factorize a joint distribution in an efficient way that will allow us to have kind of conditional independencies or arrive at conditional independencies. Crucially for causal inference, the conditional independency we're trying to get to is conditional on a richly structured prior. We can make the claim compellingly that the potential outcomes y0 or y1 are independent of the treatment t, conditional on, in this case, the latent factors lambda in our factor structure or in our structural equation model. So this is a very broad picture of the abstract program of Bayesian modeling in general. I'm now going to go into sort of a concrete detail about how to build a factor structure in PyMC and what that entails and how it inherently builds in a causal picture of the relationships between the variables in our model. Okay, so factor structures can be motivated on their own right, or factor models can be motivated in their own right as a kind of dimensional reduction technique, where you take a bunch, like a Y data set, an X data set, with, so in our case, the data set we're going to look at, it has nine columns. It has 3 columns related to, we're going to argue, related to the idea of like a personal adjustability, 3 columns related to scores of personal riskiness, and then 3 columns related to achievement. In this case, it's academic achievement, so like scores on reading, arithmetic, and spelling. So what you might like to do if you have a wide data set is just try to wrap up some of the complex multivariate rows into a simpler representation. And you can use factor structures to do that. In a confirmatory factor analysis model, what you're trying to do is sort of wrap up similarly or thematically clustered measures in your data set. And you're treating that move as a way to sort of cluster similar things that are measuring the same thing. So factor structures are kind of a confirmatory factor model in a SEM setting is also called a measurement model. The idea here is that you're actually trying to measure a kind of abstract construct or a latent construct, which is imprecisely measured by the observed data that you have to hand. Confirmatory factor models take a wide multivariate data set, wrap them up into one or more latent constructs. And the argument is that our theoretical interest in the problem is actually around the relationships between the latent constructs rather than the observed data points, because the observed data points are sort of imprecise measures of the latent construct. And the action is actually happening at a higher level. So in our case, like I said before, we have 9 variables of interest. I'm sorry, 9 variables of interest that are measuring, we argue in this model, 3 different latent constructs. One is measuring sort of scores of adjustability. One is measuring like SES or verbal skills is like a measure of risk. And then the third construct is measuring achievement, which are just scores of arithmetic, spelling, and reading. This factor model, this confirmatory factor model, can be represented in this Bayesian setting by conditioning on a very richly structured prior with these different components. Crucially and importantly, the lambdas for the factor weights and the KSI term here, psi, for the draws from the latent constructs. We're going to operationalize this model as a set of 9 normal distributions that are functions of these latent constructs, psi here and lambda. And what that means is that we have 3 constructs, which is lambda 1, 2, and 3 in this instance, and we allow the observed data points, the 9 columns in our data matrix, to load on each of the factors, three columns for one for each factor. Is there questions now on that? Because I know I've just thrown a lot at you. Sorry, I can't see the chat at the moment.
There is a question on frequentist SEM. It says there is notion of formative and reflective constructs slash factors? Is there a way to estimate formative constructs in Bayesian way?
I mean, there is no the Bayesian setting, like there's no substantial difference between frequentist structural equation model and Bayesian structural equation modeling, except for the estimation routine that you do it. Theoretically, they're not distinct. It's the same type of model. So any sort of factor that you can interrogate in one, you should be able to interrogate in the other. Is that okay? See if that's formative or reflective constructs. Yeah. Okay. Yeah, I should flag, by the way, that I'm not an expert, by the way, in structural equation modeling, but I have implemented these in PyMC, and that's kind of the motivation of the talk here. And there are a whole wealth of structural equation models, longitudinal structural equation models, which I've never touched before. So like, if you want to go deep into structural equation modeling, I might not have the answers for you, but like do throw questions at me anyway, just in case I do. Okay. In code, the factor model looks something like this, right? So you specify your the variables in your data set, which are going to be indicators for one of your three factors in this case. You also allow names for each of the three factors that you're going to build from the 9 variables in your data set. You define your priors on your lambda terms, and you want to make sure that the factor scores are scaled comparably. So you usually benchmark the factor scale against one of the observed variables of the, say, 3 that you're going to measure the construct riskiness with. So this means that you want to set the factor loading for one of the observed variables to 1, and then allow the other 2 to vary and estimate the factor loading of the other 2 relative to the indicator variable, which is scaling your factor. You define those lambda terms. You also define a covariance structure between your latent constructs, and you make draws then, a multivariate. Line 32 here is the important one. You make draws from your multivariate normal distribution, which is characterized by this covariance structure. And once you have those draws, you feed them forward into this sort of kind of regression framing where they're the latent draws xi are multiplied by the factor lambda 1 for each of the observed variables. You're creating a kind of pseudo observation matrix, which you feed forward into the likelihood term, and then re-estimate the posterior estimate. Sorry, you estimate the posterior distribution for all of those parameters, conditioned on your likelihood and the observed data that you have to hand. That's the sort of Bayesian modeling flow in general. At the top of your model, you're setting the priors for all the parameters of interest. How you're structuring that prior is important, as we've seen here. I'm allowing multivariate covariance structures among the prior draws of the parameters in our model. I'm multiplying them in an appropriate fashion, and then I'm feeding them forward into a likely term so that the model calibrates its estimates for the posterior distribution against the observed data. It's a fancy way of factorizing the multivariate distribution that we're interested in to recover estimates of how they interact and operate together. So what we get out of this model fit then is estimates for the factor loadings. You can see here what I talked about. The weights accorded to each of the observed sort of indicator metrics are scaled so that they have a unit 1 for each of the first indicator variables. So in our first construct, which is characterized by the 3 variables, motivation, harm, and stability, we have scaled that to the motivation metric, right? And then by estimating the factor loadings of the other 2, with other 2 metrics within that factor structure, we're looking to find similarly scaled factor loadings to determine whether or not our construct is reasonably well defined at the right scale with the same measures. Because we could, if we have a poorly specified construct, have factor loadings which are off the scale or far away from one. So it could be, if you've had a -2 factor loading, there's a good chance that the factor you're trying to construct using these two metrics is poorly measured by these two things together. Okay. So consistency of factor loadings is a gauge of factor coherence, right? And invariance of the loading scales across groups allows you to make an argument for the robustness of your constructs. So how well are you measuring these constructs of riskiness, adjustability, and achievement? Okay, so that's what I mean by a factor structure in the setting is a measurement model. You're trying to wrap up all the multivariate data points that you have, articulate them into a theory of these latent constructs and how they relate. A confirmatory factor analysis model will try and capture the covariance and correlation patterns among your 9 variables via these factor loadings and these factor relations. And you can then look at a measure of model fit that tries to back out how well the factor model that you've just fit recaptures the observed covariances or correlations in this sense. And you do so by taking the difference between the model implied covariance structure and the sample covariance or the sample correlation. And the residuals is then like the local residuals on each of these variables is a measure of good or bad model fit. Basically, you want these values to be low, close to 0. The closer to 0 they are, the better your model fit is, because it is more easily able to recover the observed covariance relationships in the 9 variables in our data set. Okay. Because it's a Bayesian model in this setting, we can also explicitly do posterior predictive checks where we push forward the posterior estimates that we've gotten for our parameters and sample from the likelihood outcome to derive like predictions, basically, or retrodictions for the data in our data set. And this is a way of us checking that we can recreate the data we started with, and our model is well specified enough to achieve that recreation. And you see here that the model is reasonably well fit to the observed data for each of the 9 metrics in our data set. Good. But the heart of the confirmatory factor analysis is not so much about the nine measures, but it's about draws from the three constructs we have. So we have draws for each individual in our data set of scores for their adjustability, scores for their riskiness, and scores for their expected achievement, with uncertainty bounds on those scores as well. We can sample the latent constructs. We can assess the measurement profile of individual outliers under intervention. So like you can find this guy over here on the far left of the riskiness score. He looks to be an outlier. We might want to look at the covariate profile he has on the 9 variables to see what it is that's sort of driving risk for this individual. It allows us to interrogate, additionally, what are the relationships between the latent components and how do they vary under pressure. And this last point is kind of the primary motivation for structural equation modeling in general. You want to be able to not just measure the covariance and correlations between all our observed data and the latent constructs, but you want to be able to tell a story about what's the direction of flow, how does each factor influence one another, and what's the causal story that goes along with that. And to estimate those models in the Bayesian setting and in PyMC, we build on this confirmatory factor model. We build on that structure. So what you see here on the left-hand side is something like the Lavand syntax for fitting structural equation models. where the equal sign with the little squiggle after it denotes the is measured by relation. So that's a confirmatory factor analysis model where we've just decided that for of the 9 variables we have in our data set, 3 load on one factor, 3 load on another, and 3 load on another. I tried to represent this on the right-hand side here as the CFA, where it's basically the lambdas load on the latent constructs. The difference between a CFA model and the structural equation model is that we also add sort of regression relationships between the latent constructs. So we want to say, not only are these constructs measured by these 9 variables in this way, but that there is a sort of determinative or causal relationship between one construct and another. In this case, we're saying that riskiness predicts adjustability, and riskiness and adjustability predict achievement. And the question then is, to what degree do these latent constructs predict one another? And how can we estimate, say, the causal effect of intervening on one of these constructs, setting it to 0 or setting it to 1, and the outcomes of interest? So were we able to intervene on an individual's riskiness? What would we predict? So that's represented here on the right-hand side by we add a structural component that allows our latent constructs to be matrix multiplied by a set of beta coefficients, which we're calling the matrix B here. And I'm going to outline a little bit now in detail how to specify that B matrix and how to incorporate that in our PyMC model. So the structural matrix that we have here on the left is this KSI term. These are the latent draws that we are drawing in our MCMC routine. We have scores, these are correlated scores for adjustability, risk, and achievement. And we want to define a matrix multiplication which allows us to sort of predict one latent score from another. And we have to do that in a kind of reasonably clever way where we define a matrix like you see on the right-hand side here. And you can kind of think of the sort of columns of this matrix as sort of specifying which are the target outcomes, or which are the target latent constructs, and which are the sort of driver latent constructs. So what you see here is basically in the first column, we want to set how are we going to predict adjustability. And we're saying that adjustability is predicted by the risk construct, but it doesn't predict itself, and it is not predicted by the achievement construct. So if we set up our B matrix in such a way to imitate this, we can incorporate that B matrix in our PyMC model and allow us to draw beta coefficients to estimate the weight or loading that riskiness does to drive adjustability. So this is how you'd specify it. It's basically a matrix which is mostly 0 with betas, except betas at the place where you want to sort of load one construct on another. I hope that's reasonably clear. In the model setting itself, it looks like this. You now just have extra parameters for the paths that you want to define. So risk to adjustability, risk to achievement, and adjustability to achievement as well. The model is exactly the same as the confirmatory factor model was before, but now you build your beta model, or you build your B model. You start by initializing it as all zeros, and then you sort of fill in the cells of the matrix as you need them to be. And then you cross multiply, or you do your matrix multiplication of the latent constructs and the beta B matrix, and you add these back to your pseudo observation matrix. 3 for adjustability, 3 for risk, and 3 for achievement, as exactly before. And then you again feed that into the likelihood as before. And this is a richer, more structured object than your previous model, but it is also explicitly encoded sort of directionality of influence in the same way that you would specify directionality of influence in a DAG. Okay. So you can then look at the same sort of measures of model fit, the residuals on the left-hand side, but also the leave one out cross-validation sort of ranking on the right-hand side. So you can have measures of local and global model fit. In our case, for our model, the structural equation model achieves better performance both on the local model fit and the global model fit than our confirmatory factor analysis model. And that suggests that by specifying the causal relationships in the way that we have, the candidate causal structure we're evaluating is pretty good at recovering the observed data. Okay. Yeah, is there any questions at this point? Just that because I know I'm going to jump a bit into the causal stuff now. Just jump down. Okay. Yes. Ordinary measures for measurement of model evaluation. Yeah, so there's lots of indices for model fit assessment. So you can have, Cronbach's alpha is there's ones, but there's also like CFI, I think, is one, and then there's like a ton of local measures of model fit as well. In the Bayesian setting, the ability to assess the posterior predictive checks is super important in general, and that's not going to be available in the Bayesian setting, whereas it is, it's not going to be available in the frequentist setting, whereas it is in the Bayesian setting. There are slight differences, but I think maybe, David, to answer your point then about the sort of formative versus reflective constructs, I don't know. I don't know if they can be articulated in the Bayesian setting. I would suspect they can, but I have not done so. Okay. Causal estimands. Okay. So the next couple of slides are sort of focusing on the causal estimand sort of stuff. And do operator. So like famously, Judea-Pearl's do calculus offers sort of rules for admissible structures that are allowable, that would underwrite and warrant causal claims. But you can barely see my face. Will I just go turn on a light? 1 second. That's a bit better. So those rules which warrant various different causal claims sort of complement the development of a structural equation model, because you want to define the paths of influence in your structural equation model that sort of minimally respect the rules of the do calculus. You don't want to draw a DAG which will deliberately confound your estimate of a causal quantity. And so in PyMC, we're able to construct these DAGs and these paths of influence across the Bayesian setting. But of course, you want to be attentive to which directions of flow you allow in your model. And we are also going to be able to then intervene on the graph that constructs our joint distribution in the Bayesian network. And that's what I'm going to show next. So sort of the analysis of a structural equation model in general is done under the sort of speculation that what if these causal assumptions were true? What I've shown you so far is that you can build these structural equation models with these rich paths of influence among them. You can evaluate that model for various measures of correctness or model fit. And that's one implication of a fitted SEM model. So it's what if that was true. But another sort of way of interrogating these models is to use the sort of do operator syntax and like try to gauge or estimate what is a causal quantity on these graphs. And so the sort of famous example from Pearl's work is like whether or not you turn a sprinkler on or off, you intervene on this DAG and you change the sort of conditional probabilities under intervention. And you can do that in PyMC. And this is kind of what I want to show next. You can do this in the context of a SEM model. So the sort of code here is like I've hidden a lot in this make sem function. But basically, if you take the sem model that you we had before, you will derive from our Bayesian structural equation modeling two things: the model definition and the inference data object, which you will get out of it. You can see the structure of the sem model on the left-hand side here, where we have the beta coefficients, which determine the paths between our latent constructs. And then on the right-hand side, you have this kind of new syntax or newish syntax for the do operator in PyMC, where you can take a fitted model, like the one we had before, use this do operator and intervene on the parameters that we have sort of derived in the first place and just set them to a fixed value, pruning the influence paths before it in the node, and so thereby achieving the sort of graph mutilation definition of an intervention that is sort of present in Judea-Pearl's work. So you can kind of see here that in the model in the model specification on the right, the beta coefficients stop being a random variable in our model, but are in fact sort of data points now instead. I set them all to 0, which is sort of an implausible setting, but it's more just for point of illustration at this point. So you can do the same with another candidate model. And this is a slightly more realistic setting. I've put these beta values out here. You can define and resample from the model under such a setting. That is, you can predict the posterior predictive distribution under this parameter intervention, under this intervention where you've done do betas equal blah, blah, blah. So you now have two models, two resampled likelihoods, where you can define then differences between the outcome y under these different intervention settings. And that's what gives you the ability to express causal estimands in this PyMC setting, where you have two intervened upon models and you can calculate the difference in the outcome variable, or in this case, outcome variables due to your interventions. And your interventions can be more or less targeted at precise sort of treatment variables in your data set. Here, I've just taken the difference between all 9, just for sake of illustration. And then I'm taking the difference or the expected value, so the mean or the expected value across all the trains and draws in my MMC sample. So we have two models refitted under different intervention conditions. We can derive causal estimands in this fashion. We can also do different kind of model. We can look at different model fit criteria, like I've seen before. So in the initial model, we had a certain sort of healthy residual plot. On the left-hand side here, you see a reasonably healthy residuals plot. And on the right-hand side, where I've set everything to 0, all the beta parameters 0, we have a deeply unhealthy set of residual plots. So what I'm trying to say here is that, like, this is kind of my conclusion as well. This PyMC setting for causal inference allows you to fit a complex joint distribution of variables, allows you to structure or factorize your model or your Bayesian network in such a way that you can represent the sort of conditional independencies which will underwrite valid causal inference. And you can then start intervening on the Bayesian network to define these causal estimands of interest and assess your model fit or viability under such interventions. So if you're going to assess a causal claim, what would happen under such and such a circumstance? You want to be able to assess that, but you also want to be sure that that circumstance isn't too far from reality, right? It should be a plausible counterfactual setting. And so there's a nice quote here from Bolin and Pearl in their 8 myths about causality in structural equation modeling. That's like SEM is an inference engine in this case. It takes 2 inputs, qualitative causal assumptions and empirical data. And the point is to derive the logical consequences of that setting, of those settings, your assumptions about the relationships in the network and the data you have to hand. Fitting your data does not prove that the causal assumptions are correct, but it does make it tentatively more plausible if your model is well specified. So this is a type of inference engine that you can compare, kind of interestingly, I think, to like this picture from the Dr. Seuss. It's the, if you've ever read it, it's the Sneetches. They have this inference engine where you go in on one end and you come out with a star on your belly. So it's a different type of inference engine. You're not finding significance at 3 stars, but you're building sort of a model of the situation, drawing inferences from the implications, and trying to evaluate whether or not the causal claims determined by the causal estimates determined by your model are good and sound inferences which to pursue and build on. But the project is inherently one about building credibility about your causal claims rather than sort of rubber stamping it with a mark of significance. It's a different type of inference engine than that. Anyway, that's I think that's me. I'm going to conclude there. Happy to answer any questions that might be remaining. Is there a way to estimate something like frequentist multi-group analysis in a Bayesian SEM? So like you can definitely have hierarchical models. And in fact, kind of Bayesian modeling shines at hierarchical settings. So like, I mean, I've not implemented them myself, but I've seen them implemented. I'm not entirely sure that's multi-group analysis, but you can have hierarchical versions of a SEM model that have extra coefficients that determine group level differences. So like you mentioned for gender, I'm almost certain you could implement the model I have there and add an extra factor for every observed respondent who is either male or female, and allow that extra sort of beta adjustment to vary based on that group level structure. That's kind of the hierarchical modeling in that fashion is one of the sort of bread and butter things about Bayesian modeling. So it's almost certainly doable in the SEM setting, but I've not done it myself. I hope that's clear. Okay.
Okay, yeah, so if no one else has questions, I think we can end it here. Thanks a lot for attending, everyone. And thanks, Nathaniel, for being a speaker today. And yeah, hope you have a good rest of your day.
Thank you very much. Have a great day. Thank you.
Bye.